Good afternoon, everyone, and welcome back to Foundations of Algorithms. I'm so excited to see you here on what is my last day teaching all of you for a couple of weeks. I know you'll miss me just as much as I'll miss all of you, but don't worry, we'll get through it. And of course, there is the mid-semester test, which we just announced that's coming up in 2 weeks' time. So keep your eyes peeled for an announcement on that. So where we left off yesterday was we'd gone through all of this effort to try and sort an array. We'd come up with this kind of complicated recursive algorithm, Quicksort. We did a few demos with it. But why are we even bothering with it? Does anyone have like a sense of why I'd want to sort something in the first place? Yeah, Oscar.
It makes it easy to search.
So it makes it easier to search. Let's dig into that a little more and see why that is. So perhaps we want to find some specific item in our array. So if sorting it first is going to make it easier, let's try that. But how much does it actually help? And that's going to be the motivating question for today. So we're looking for an item in a set of items in our array. And we could just go right ahead and do it. The array is as it was given to us. Or we could sort it first and then look through the array and see if that speeds things up. So remember, at the beginning of the week, we did all this hefty work as well on big O analysis. And we're now going to apply that to a specific instance of the problem with searching through both a sorted and an unsorted set of elements. So let's do the comparison, starting off with the unsorted version, the version that we think is perhaps going to be a little less efficient. So here's the statement of our problem. Find a value x in an array of length n. And because it's my last week of teaching, I did bring along my special friend again today for the last time this semester. Big Blue Brain is back. So Yuvani, do you want to take the lead? Yeah, I can see it. You want to take it. And I'm going to need a few volunteers again. Wait. This is the number that Big Brain Yuvani is going to be looking for. Is Big Brain Bronson here today? No. Okay, so here's the number. You see it?
Am I allowed to see it?
Yeah, you're allowed to see it. You know what number you're looking for. That's the whole point of the problem. You know what you're looking for, you just don't know where it is. Yep. Okay, so turn your papers around, because our computer is only going to be able to look at these one at a time. Need one more. Okay. And let's make sure to face the class, even though kind of at an angle, so that everyone can see what we're doing. Everyone sees the number we're looking for? Yep, okay. Yuvani, so what is your strategy? Let me grab the microphone so we can all hear you a little better. And I want you to tell the class how you're going to do this. Obviously, you're the most intelligent person in the room, so I'm looking for some advice. Can you tell me, Dr. Yuvani, how are we going to find this item?
I suppose I already know what my value is. So
you know what we're looking for, and this is still not
just sort of
on?
Evaluate if they're
there we go.
Equal to each other.
Okay, so we're going to look and see if what we find is equal to the thing that we're looking for. Mm-hmm. So let's maybe go ahead and do that. Okay, who are we going to look at first?
I'll just start at the beginning of the array.
Why are you going to start at the beginning?
Because then I can go sequentially down.
That seems to make sense. And we don't really know, we don't have a good guess of where it is either. All of them are kind of the same. It's just closed doors, right?
Yep.
Okay, so let's do that.
Hello, can I see your value?
Okay, what do we do now?
My value is not the same as that one, so I'm going to flip that over.
Okay, so flip over. Sorry, you're not who we're looking for. Let's keep going.
Hello, can I see your value? 1 is not 15.
Okay, I think you know what you're doing now. I'm going to let you take the microphone, and now we can walk along and keep doing it.
Hi, can I see your value? Thank you. 1 is equal to 1.
And so we're done.
Yeah.
Okay, now I'm going to change things up. Go to the back at the end.
Okay.
And I'm going to take these numbers, and I'm going to move them around. And I'll swap some here. And who doesn't have a number now? Young doesn't have a number. Okay, so let's do this process again. And you can go through it a bit quickly. I am very confident in your abilities.
Thank you. Okay. Hi. Nope. Nope. This is my value.
So was that the fastest you could have done it?
I probably could have sprinted, but...
Okay, so we could have sprinted. But how many things would we have had to look at? Let's say there are n items. How many items did you have to look at?
All n.
All n. Okay, so is this our best case?
No, this is the worst.
This is the worst case. And what would have been our best case?
If the first value was the number 1.
So if the number 1 was over here, then we would have only had to look at one thing, so that would have been really fast. What about the average case? Can you take a guess as to what that might be?
Like in the middle?
Yeah, so if we figure out, well, let's sum up how many steps we have to take if it's there, or if it's there, or if it's there, or if it's there, we can actually easily do the computation. You can do it on your own to figure out that the average case is going to be searching halfway through the items. If we have n items, how many is half of our n items?
Half n is.
Yeah, half of n. That's perfectly right. Now let's go back. That sounds like a stupid thing, right? Half of n is half of n. But remember, we're doing asymptotic analysis here. We're doing big O. And 1 on 2 multiplied by n, this is for someone else. I'm going to see if there's anyone else as intelligent as you in the crowd. Is 1 on 2 multiplied by n, what's the big O of that? What's that big O of, sorry? Yeah, Ahmed. It's n. It's big O of n as well. So we actually haven't really made a saving in that case, in our average case. Our average case asymptotic behavior is going to be the same as our worst case asymptotic behavior. They're both proportional to the number of items you have. Because if the number of items you have doubles, it's still going to take you double the amount of time, even though you do have that 1 on 2 constant out in front for an average case. Okay, so that concludes our demo of the very basic unsorted search. So I'm going to get you all to remember, take your numbers back with you to your seats, and we're going to bring you back in a couple minutes to see if we can do a little better. And let's have a round of applause now for Yvonne. She's going to be back, but... So the intuition here, why is this big O of n? Well, it's because if you don't have any clue as to where the thing is, and it could be in any of the n elements, let's say it's at the end, well, you're going to have to look at the elements to make sure to find it. You can't see them all at once. This is just like the people had their papers turned around. The computer can't see things all at once. It's going to have to look one by one by one. And so in the best case, in the worst case, you're going to have to look through all of the different items to check, is it behind door 1? Is it behind door 2? Is it behind door 3? So this is our algorithm represented in the pseudocode, which we've now become familiar with. And we have our usual 2 questions about this. So is it correct and is it efficient? We've just talked about the efficiency. So now let's move a little to talk about the correctness. It seems to work. It's sensible. But we need to come up with a more rigorous argument. And what did we do yesterday to make a rigorous proof of things? We used a assertion. Yeah, and along with the insertion, we had the other thing connected to the assertion was an invariant. Yes, that's right. We had something that we know is going to be true consistently throughout our program until such time as it concludes. Okay, so here's our algorithm. Let's step through it very quickly. We have a variable I that starts off at 0. It goes up to n. And while it is less than n, so while we're still iterating through the array, while we're in the bounds of the array, and the current item that we're looking at in the array is not the one we were looking for, is not, say, that number 1, move to the next item. If the next item is in fact what you were looking for, then this loop will conclude. If you are at the end of the array, if you've gone all the way to the end and you still haven't concluded early, then that means the item is the item's not found. It's obviously not there. If you've gone through everything and you haven't stopped finding the right thing, then it's not there at all. So this is a heuristic version of the argument, but let's try and make it rigorous. So let's use an invariant. What's our invariant in this case? So we're going to call our invariant P. This is a different P to the ones we've seen in other lectures. This is just a new statement. So our invariant this time is a little simpler than the quicksort one. What we know firstly is that our value I that tells us which item we're looking at, that's got to be confined within the bounds of the array, because obviously we can't look at the negative 1th item in the array and we can't look at the n plus 1th item in the array. Those items don't exist. So that's the first half of our invariant. Again, kind of simple and stupid sounding, but it's a core part of our argument. And the other thing we're going to say is that we know that if we haven't stopped, if we're still going, then we haven't found x yet. And another way of saying that is the value x that we're looking for wasn't any of the elements up till this point. And this is just the way of writing it. We say that x was not one of the elements between 0 and the last item we looked at, because if it was the last item we looked at, we would have stopped. Okay, but what do we compare? What's the worst case? We've talked about this. This was O of n. Our average case was still O of n. We could hope for the best. We could hope that our item is the very first one in the array, but that's probably going to be a false hope most of the time. How often is the thing you're looking for when you lose something in the very first place you look? Almost never. It's always in the last place you look. And have a think about why that is. So always plan for the worst case. Why? Because you are not always in control of the array elements. You might not have put them in the order that you wanted in the first place. In fact, sometimes the inputs to your program might even be coming from someone adversarial, someone who's trying to trip up your algorithm and make it run as slow as possible. Maybe they're just trying to stop you from using your computer. So planning for the worst case is always advisable. So the question is, can we do better than all of this? Linear search seemed to work. It ran just looking at everything once. Can we do even better than that? Yes, but don't. That was a rhetorical question. OK, so I'm going to need Giovanni. I'm going to need your big brain again. Where'd the brain go? The brain went over here. And this is your shining moment in the class. Hopefully mine too. And we'll give you a microphone. So over here, I have a sorted list. How many of you have seen one of these before? Do we still know what it is? OK, the old folks in the back know what it is. This is a telephone directory. One day, they're not even going to keep printing these. But for now, I managed to get my hands on a telephone directory. And this has a list of all the people in Melbourne 2022 and their phone numbers, at least the people who had landlines. So I could look and see that CPREL is at, can you read me their phone number? Yeah, just that one there. Doesn't matter. Just read it out.
94352858.
And then after CPREL, we have?
Prela M.
OK, so this seems to be in order. It's got people's names and addresses. Let's say I am looking for my friend, let's say Cohen. I'm looking for an A. Cohen in here. So I'm going to start looking through. And OK, is there a faster way I can be doing this? Adams. Mr. No, Adams, Arjit. Giovanni, what's going on? How could I do this a bit faster? Aladas, Asquith.
You're going alphabetically as is. Are you looking for A. Cohen?
Yeah, Cohen. And this is done by last name in here.
You can start at C instead of starting with A.
But I don't know where C is in this thing. I'm going to keep going. Brooks, Bright. I have an idea. Why don't I skip a few pages at a time? OK, I'm now at Carbon, Delane, MSO.
Go back.
Go back?
C.
OK, I can go back. I'll go back a few pages. Elliot, Dembo, Delane, Day. Give me some help here. Demoli, Cornus. OK, why don't you tell me how you would do this? If you want to find Cohen in here, what are you going to do?
I would go to C. But I don't
How do you know where to go to C? How to go to C? What's the first thing you do? So I hand it to you.
A and, okay.
So you're going to start at A? Or what are you going to do? Show me what you do.
I'd open it.
OK, you'd open it. So where should I open it
If
to?
I know that A is before C, then I would
Oh, so there's something about this before then process. So I'm going to open it. And where should I open it to? Let's say halfway. Halfway makes sense? OK, halfway makes sense. I have Kimto and Kist. Let's say this is halfway through. What am I going to do now? Is Cohen before or after Kimto?
I know that it's before.
It's before, OK. Well, I guess I don't need that half of the telephone book anymore. OK, so I guess I could do that again. So Fenton and Farah.
Yeah, you can still go ahead. So.
OK, well, I guess I don't need this half. Half again? Let's try that. We've got Brugley and Buckney.
Now you're going to go forwards.
Forwards, OK, so throw out that half. Day and D.
Go ahead.
Go ahead.
Sorry.
C is after D.
Back.
OK, go back. Let's do that. And let's do this a few more times. There's Cherney. Oh, I know that family. OK. And now I go halfway again. Let's say it's about there. I'm at Conti. Halfway again.
Where are you up to?
Conti? Yeah, so let's go halfway. Keep doing this a few more times. And eventually, after not very many steps, I will have found Cohen. So let's compare this to when I was starting at the beginning. Another round of applause for Giovanni, who successfully guided us through. Took a minute, but we got there. Now, you'll notice that the number of times I had to rip the book in two is pretty bounded. Let's say I had 10 pages, and I ripped the book, or let's make it 8 pages, and I ripped the book in two. How many pages am I left holding in my hand? Emmeline? If I rip 8 pages, an 8-page book in two, how many pages do I have? I have 4 pages in one hand. And then if I split it in two again, 2, and then again, 1. And what do I know if I've got 1 page in my hand? Yeah, it must be the right page. And so the number of times that I can do this is really limited. And each time I'm going to halve and halve and halve and halve again. So if I have a given number, let's say I have a number n, how many times can I halve it before I get back to 1? That's going to be log base 2 of n. So this gives us our running time for binary search. Even in the worst case, we know that we will be able to do at most log 2 of n rips before we get back to 1 page. And if we're on 1 page, either the name is not in the phone book or we have the right page. And this is the power of binary search as compared to linear search. Because log n is much, much smaller than n, as we saw in our graphs earlier in the week. So let's take more of a look at this and go back to our pseudocode. So this is, again, a schematic version of the algorithm. We'll look at it in C in a little bit. Let's say we're looking for our friend in the phone book. Open the book to the center. Let's just assume that there are a fixed number of names on the page, because obviously if Cohen isn't the first name there, you'd have to still look down them. Because they're in order, we could actually do what on the page? We don't need to look through all of the names on the page. What could we do? So we could binary search the page as well, but let's ignore that for the time being. Let's just say there are 10 names per page, so each page is only going to give us an extra 10 steps of work. Okay, because every page is the same number of names, but different phone books from different years might have different number of pages. So our procedure then is if the friend is earlier in the book, throw out the right half. If our friend is in the later half of the book, throw out the left half, and just go back up to the top and rinse and repeat. Now, if I have this go-to where I'm going up to the top again and again and again, this is really what kind of control structure in C? It's a, what's that, Quen? Recursive. So recursive is a really good answer, but here is our representation of that recursive version of it here. So one really common way of representing binary search is this recursive solution, where we're going to do the same procedure again and again, just on a smaller amount of data. So let's calculate our efficiency using our big O notation from before. We have a constant number of names to look through on each page. And every time we are halving the amount of data we have. So just like, remember Hanoi, how we did this kind of recurrence relation for Hanoi, for the Towers of Hanoi? Figure out how much work there is to do on any given level, and then you add to that the smaller version, the amount of work that it took to do the smaller version. So in this case, it's going to take half the work to do the smaller version because we're doing it on half the data. So how many recursive calls will there be? You've already told me this. Maximum of, yeah, maximum of log 2n, and at each level we only have to do C work. So there is another way of puzzling that out. We get log n equals k, and you can see this on the slides. So we get C multiplied by log n, because at each level we have to do C work. And then when we're at the final level, we just do C work. So there's our plus C at the end, which gives us overall log n. Great. Now we have to do the other half of our proof. So we know how long it took to run. We still have to figure out if it's actually correct. Obviously, that seemed to work, and we made a pretty good argument. Giovanni really helped me out there. So let's do the same thing we did before. Let's make an invariant. So by now, you're used to seeing this. We have our 2 boundary variables that we're going to use, and we're going to say that our boundaries for which parts we've thrown out are still in the array. So low is the boundary for everything we've thrown out to the left, and high is everything we've thrown out to the right. And obviously, we can only throw out things that are in the array, so it has to be between, both our boundaries have to be between 0 and n. Then we have our 2 other clauses, and these are the ones that are unique to binary search. Our items should not be in the left eliminated section, and our items should not be in the right eliminated section. If our item is in neither the left eliminated section nor the right eliminated section, where must it be if it's in the array? Yeah, in the middle bit, in the bit we've got left, and that's exactly the thing we were doing. So this is, again, it feels simple, but really, really powerful. So set low to 0 and high to n. So the bits that we've thrown out at the very beginning are nothing. We're starting with a full book, and so we haven't excluded anything on either side. We haven't thrown anything away yet. And what happens to low and high as the algorithm progresses? Are they going to get bigger or smaller? Are they going to move towards each other or away from each other? Yeah, Angela. They're going to move towards each other. As we throw bits out, low is going to cover more that we've thrown out, and high is also going to cover more stuff that we've thrown out. And what's going to eventually happen? It reaches might not be the center, but they're both going to grow, and we get down to what? We get down to one element, and so when we're down to one element, we know that either we only have two possibilities,
It's either what we're looking for.
or what's the other option?
It's not there.
Or it's not there. Flo, did you say that? Yeah, good on you. So the two ways that this algorithm could finish is either we've stopped because we've actually found the thing we're looking for, or we've stopped because the item was never there in the first place. So let's use our invariant and prove it. This is a version of the code written in a language a little closer to C. So let's assert our invariant, which we know is true at the very beginning of our function because of the way we've set it up. And we know that low is less than high because low started at 0 and low started on the left side and high started on the right side. So they shouldn't have crossed at this point. Then what we're going to do, we're going to pick a middle point, m. And we just set this to the middle by calculating the difference between the boundary from the stuff that's remaining on the left, the boundary of the stuff that's remaining on the right, and we go halfway between those two boundaries. And then what we do, we assert our proposition again, and that our midpoint is in the middle. And obviously, by the way we've computed our midpoint, assuming all of these are positive numbers, we know that m must be in the middle just because of the way we've computed it. And we also haven't done anything else that would have violated our invariant over here. So we still know that the element we're looking for wasn't in the left half. Okay, so now we have our two if statements that rely on the item we're looking at now, the item in the middle. So let's look at this item in the middle, a brackets m. If our target x, if our target x is smaller than the thing we're looking at, what do? Emmeline? Yeah, we're going to throw away the right half and look at the left half. But because we're now inside the computer, we can't just throw away the book. What we're going to do instead is just move our boundary. We're going to move our boundary on the right to exclude everything up until that point because we know it wasn't in that half by definition. Because this thing is sorted, it can't be in that half, which allows us to move high, to set high to m, and we can assert our invariant again. Let's go check our invariant. Okay. We still know that low is smaller than high because we haven't touched that. And we know that they're within the bounds of the array. We know that it can't have been in the right half. And we haven't touched the left half either. We haven't touched the boundary on the left. So our assertion must still be true. We now do the exact same thing just for the other side. I'm not going to run through it because the argument is identically symmetrical. It's the same thing, just you're throwing away the other half instead. Finally, we have our else case. If the item we're looking for, if the item we're currently looking at is not smaller than the item we're looking for and not bigger than the item we're looking for, what must it be? Yeah, it must be the item. Thanks, Max. So we must be looking at the item that we want. So we know that our invariant is still true. X is not smaller than the current element. It's not larger than the current element, so it must be equal. Therefore, X is the current element, return. What is my other case? Flo said this before. What's the other way my algorithm could terminate? Yeah, if it's not there. So in this case, I will keep halving, keep halving, keep halving. And so if the way I can keep halving is only until low is less than high. When low is now equal to high, then the algorithm terminates, which takes us to a final statement in our proof. So we have our invariant, but now low is bigger than or equal to high, because this is how we know we've exited the loop. This means we've thrown away everything. Our boundaries have crossed, And so we've thrown out absolutely everything that's left, which means by definition x must not be in the array, and so we return not found. And that is all of binary search. Seems relatively straightforward. This is a version of the code without the assertions. You can fit it on a simple page. You think, surely, you know, Shannon, Dr. Connor, you've been studying algorithms for a long time. Surely you'd be able to code this pretty easily. We'll get back to that in a minute. So this is John Bentley, who's a famed C programmer, and he ran a study where he asked a whole bunch of really competent programmers to write this pretty simple algorithm. Just these lines over here. 90% of the programmers found bugs in this program. And obviously, I was going along my PhD. I thought I was better than all of these programmers. And so my PhD advisor got, or one of them, got all of his PhD students in a room, and we replicated the experiment. He said, I will give $50 to the PhD student who successfully writes binary search correctly the first time on the whiteboard. And what would you believe it? Not a single one of us managed to write it bug-free after half an hour. And so this actually goes to the reason why we're doing this whole correctness proof in the first place. One thing that not one of us in that room did was use assertions and invariants to try and make sure that our code was correct. And so this should be, it was very instructive to me, and hopefully will be instructive to you, that the point of these correctness proofs is not some abstract mathematical pie in the sky thing, as interesting as that might be. It actually helps you to write correct code, to do these proofs, and to weave the proofs into your code. And remember, last lecture we talked about a statement in C that we could actually use to ensure this. What was the statement? Yeah, it was assert. So the program, when you run something with an assert, you give it a condition, and if the condition is false, what happens? It crashes. The program crashes. And so this gives you an assurance that if the program hasn't crashed and your proof is correct, that you've solved it correctly. So now we've done all the hard work for binary search. Our array is sorted, which takes us to yesterday. We had quicksort, but we hadn't done the analysis. So let's go back and do the analysis. Remember, we had our partition function, and I also promised that I would never again say what the partition function did. So I'm going to take a drink of water, and you're going to tell me what the partition function does. What does it do in quicksort? What do we put over there?
Bigger.
Well, other way around.
Smaller. Bigger. Same. Bigger.
Yeah. So on the left, we have, say it really loud this time so we can hear it.
Smaller. Smaller. Same. Bigger.
And this is all our partition function does. So let's calculate how long it'll take us to move all of the n items over to their correct places in our partition function. So let's assume for the sake of argument that we have this variable t, and we have our boundary on the right, fg, and we have our next item as well, and there's some gap between them. And t is just going to measure the gap between the current item we're looking at and our first greater boundary. And so let's set t0 to be equal to n, which is just the length of our array that we're partitioning. So at each iteration, the partition function is going to either move us along to looking at the next item, or we're going to move the first greater boundary further along. And so how many times can we do this? I mean, it says it on the board. How many times can I move either that one or that one up until they touch? If I'm starting at the beginning of the array and I'm starting at the end of the array, how many steps can I move the things towards each other until the two touch? N steps, because if I move this one, next time I could either move this one more, or I could move the other one, and I can only do that n times because my array is only of length n. So partition is O of n. What about quicksort itself? So quicksort, remember, we had three steps, or four-ish steps. What were the steps in quicksort? Someone remind me? The first thing we do is choose, what do we choose? We choose a pivot. Okay, after we've chosen the pivot, we use partition. So what do I put there? Smaller. And then I recurse. So I do the same thing. I take the left side and I choose the pivot, I partition, and then I recurse on the left side and the right side. So this gives us a recurrence relation as above. So partition, we said, takes big O of, it takes n steps, and then I have to do the recursion on both of the halves. Each half is n on 2 elements, and I do it twice. So that's n plus 2t n of 2. and I'm going to ignore the floor function here, which is going to account for the fact if I have an odd number of elements in my array. And so this ends up being n log n in the average case, and in the worst case, it's going to be big O over n squared. And those proofs are a little more complicated, so we're not going to expect you to do them in this class. Now we're finally ready to look at our code demos. We're going to look at binary search, then we're going to do quicksort, and then we are mostly done with our sorting and searching algorithms until much later in the course. Let's start off with binary search. Now remember, this is the horror function. I would strongly encourage all of you to try writing it yourself from scratch, just to see if you can solve the puzzle. And I'll tell you what, for the first person who successfully codes a working implementation of binary search without reference to this code here, you'll get a t-shirt transfer for a Foundations of Algorithms t-shirt. Okay, so we have a few new things that we're going to be doing in our binary search function. We have some hash defines as before. This thing is new. It's a type def. So what a type def is going to allow us to do is it's going to allow us to create our own type. So we've seen ints, we've seen chars, we've seen all kinds of different types. Now we want to make our own type. Unfortunately, for this demo, our own type is going to be pretty boring, but it'll still be useful. We'll call it data t, just data type. And it's pretty standard in C when you have a type to call it something with an underscore t, because that indicates that it's a type. And what is data t? Data t is just going to be an int. They're the same thing. Data t is just a new fancy name for it. And I'm going to have created that. I'm going to have told the compiler about this new type with this line over here. Now, it doesn't seem very useful yet, but we'll come back to this in a moment and understand why wouldn't you just use int? Keep that question in mind. OK, now we have a comparison function. So all this comparison function is doing is it's taking in 2 pointers to data t. It's dereferencing them and comparing the 2 values, 7 and 8. These are our 2 locations that we're dereferencing to. OK, so I dereference to 7, I dereference to 8. Then what do I do according to this function? Well, yeah, we could either do it. Either one of these could be x1 or x2. Let's say 7 minus 8. 7 minus 8 is -1. What if we switched it? 1. So what's this function actually doing? It's CMP. What is CMP probably short for? Compare. It's comparing our 2 things, our 2 data t types. But we're still a little uncertain. Why do we bother going all of this effort? Why don't we just compare things directly like we did before? Again, another piece, another clue to why we're using a type def. Let's keep that in mind, and we'll get there in a minute. OK, now I have my main function. We're going to skip over that. And finally, our core binary search. So it's just as we saw before. Have a mid, our middle item. We called this m before, and an outcome, just success or failure. And our key must always be between low and high. So if low is bigger than high, obviously we're outside the bounds of the array. That's our base case, again, in recursion. Choose the midpoint. Now we're using the compare function. What we said the compare function does, it tells us which one is bigger. Because if the bigger one was the first one, then we'll get a positive result. If the bigger one was second, then we'll get a negative result. And so outcome will just be a variable that's positive if the left one was bigger and negative if the right one was bigger. So it's doing the same thing as our comparison was doing in our other binary search code. It's just doing it in a way that works. We have our 2 recursive calls. And you'll notice the way our recursive calls are working is all we're doing is we're changing the bounds that are being fed into binary search. So the second and third parameters are low and high. So when I split it, instead of passing the original low and high, the new low is going to be the midpoint plus 1. And the new high point is still going to be the high point. That's if it was on the right side. And if it was on the left side, my new low point is going to be the same low point as before. And the new high point is going to be that middle, because I'm going to throw out everything on the right. So by carefully manipulating my low, high, and mid, I'm able to tell the algorithm which bits of the computer's memory are actually valid to look in, which parts of the array we're still active in. So we're ready to give it a run. And binary search does mostly what we'd expect. So now let's try our quicksort algorithm. So here is quicksort.c. Oh, sorry, totally forgot. So why did we use our whole complicated type def thing? What would happen if I change this to char? Anyone have a thought now? We have our two clues, so I've used a type def here to change, to make data t an int. And then over here, I haven't had to specify what the type is. I've just done a subtraction. So if I change this to char, my program might still work. So what's the point of having this data t thing? What does it allow me to do very quickly? And Olivia, do you have an idea? No? Okay, Karen, wait a minute. Let's see someone else perhaps. Yeah.
So maybe you need to change the variable in another part of the code. You only need to change it once rather than changing it for like every single line.
So let's say I've written this long bit of code that's specialized to handling integers, right? And I've written int all throughout my code. But now suddenly I realize that actually I want to be doing search on characters. And I want to reuse my code, but it's going to take me a long time to go through and change all of the ints to chars. And in fact, I can't do that with all of the ints because I'll have other ints that weren't part of that whole process. They're just other ints that I was making in my program. So find and replace won't do it either. So what this is allowing me to do is allowing me to abstract out the type that we're working with. So instead of having to worry about the fact that we're working with int types, all we have to make sure is that our type successfully is able to use this compare function, that when I minus one from the other, that the computer program is going to treat that in the same, in a consistent way. So now if I were to change this type to char, I could write a new main function that does all these searches on chars without a problem. Okay, so now we've done our warm-up, let's look at Quicksort. And Quicksort is going to do more or less the same thing as we just saw. It's going to be polymorphic. It's going to be able to run on different types, which is what that word means. By just changing this single type def up the top, we can make our Quicksort run just as easily on characters or on longs or on doubles or anything like that, as long as we've set this up at the beginning. Okay, so we have our CMP function again. And finally, here's our Quicksort. We have our first FE, we have FE and FG, which we've just called first equal and first greater in the code. Because it's a recursive function, that's our base case. So when we only have one item, then we're looking at the item we want. Choose a pivot. Now we'll see why we make this a function in a second. Then we do our partition function, which I think we're done repeating it for the last time in this class. We're not going to say what it does ever again. And then we recurse on the left side, recurse on the right side. So let's give this a run, and this code will be available for you to download if you want to go into the details of it. One notable thing that we're going to do is we are going to choose the first item in the array as our pivot, A0. And I've made this choose pivot function just to illustrate to you the impact of choosing different things as the pivot in each layer of Quicksort. So let's compile that. Okay, seems to be taking quite a while. That's not good. We've got another 10 minutes or so. Oh, we've got something. Okay, 20 runs. We've got, how many sorted items? We've got 100,000 sorted items, and this is taking 318 comparisons to put one item into place, and 954.2 copies. That sounds like a lot of work, and this is still running. And this was on items that are already sorted. Okay, this is no good. I don't know. I could give up. We could go home, but I've got another idea. Let's choose a different pivot. Okay, now I'm going to choose as my pivot the midpoint of the array. Maybe this will be better. Maybe this is a better choice for a pivot. Let's see what happens. Oh, that's a lot faster. In fact, that algorithm ran, let's take a look. 318 comparisons per item and 16.6 comparisons per item. Those are different orders of magnitude. So evidently, our choice of pivot is having a really significant and major impact on the performance of our code. Okay, let's try one more experiment. So my last experiment is with a random pivot. Okay, this one's also pretty good. Now let's scroll up and get some more of those details. So here I have a few different types of arrays that we're comparing. With the first one where we were picking the 0th element in the array, obviously no good. Even for a sorted array, it took a long time. But now we can compare what happens if we give Quicksort an array that's already sorted. What happens if the items are in reverse sorted order? What happens if the items are all the same? And what if the items are randomly generated? And let's compare our midpoint pivot over here to our random pivot. So when it was already sorted, the random pivot looked like it took a bit more time. When it was reverse sorted, same kind of deal, took a bit more. When the items were uniform, they're the same. And then on the random items, our random pivot just edges it out. But you can still see that choosing our midpoint worked for some particular scenarios, and then choosing the random one worked for another scenario when the items in the array were actually unpredictable, when they weren't like in some special order, either sorted or reverse sorted. The random choice of a pivot actually ended up a bit better. So that's telling us something about which pivot we should pick based on what we actually expect to be in our array. And which of these was obviously a clearly worse option? Yeah, Josh says picking the first item in the array, or the 0th item in the array, as our pivot was never a good choice. So despite all that hard work that we did with, who was it? I think it was Bronson that did Quicksort. So despite Bronson's hard efforts to get things in the right place, we needed a new algorithm, we needed a new choice of pivot. So we've got a few minutes left, and let's talk about the efficiency of Quicksort with different choices of pivot. So it turns out that actually solving this problem with a random array to figure out the average case of Quicksort is really hard. I mean, it can be done, you can do the maths. But if we are assuming that our array is already random, then maybe choosing the first element as our pivot would be a good option. Turned out not to work so well in practice. We just did that experiment. And our arrays are often not entirely random. Arrays, when you're sorting, you don't normally try and sort something that's totally out of the blue. You might be sorting something that has some sort of natural distribution to it. And so it turns out that this notion of randomness and relying very heavily on the randomness of the array might not be the best way to choose the design of your algorithm. So what we did instead was we chose a pivot randomly, which would give us more of an advantage in this instance. So we do a little bit of mathematics, and what do we get? We get this expression, 1.44 n log base 2 n plus O of n. So this is still n log n for our quicksort. We could choose the midpoint as the pivot. This turns out to be hard to analyze, so we don't have a nice closed form expression for you for it. We could have been fancy and done all these other mechanisms to try and choose our pivot the best for our data. But in practice, it turns out that choosing our pivot randomly really is going to end up being the best way to handle most sorts of data, just by our experimentation. And this illustrates kind of a different way of approaching the problem. So we did all our fancy analysis, we did our big O analysis, but what really mattered in the end as the engineering part of computer science was actually getting out there, testing it on some data, testing it on what we expect to see, and that gives us an indication about how we should actually design our algorithm. So there are all these different steps that we needed to consider. Is our algorithm correct? Is our algorithm efficient? Then we needed to think about how do we write the implementation? How do I know my implementation is correct and not just my theoretical algorithm? Then what kind of data is my implementation going to get? What does that say about the way that I should design my implementation? So we've chosen in the end, through our experimentation, through this whole long process of designing the algorithm, implementing it, and then experimenting it, we figured that we could just choose a random element for the pivot. And this ended up working quite well. So now the input sequence doesn't really matter for our analysis. We've got our same worst case big O analysis. And I'll leave you with a question for today. Can we do sorting in, sorry, that was for, we had average case n log n. So the question that I'm leaving you with for today, and that I'll leave you with until I get back, is can we do sorting in worst case n log n and not just average case n log n? And with that, thank you very much, and I'll see you all in a few weeks.